Economic dispatch solved problem 5. A 2-bus system shown if 50 megawatt is transmitted from plant 1 to the load, a transmission loss of 10 megawatt is incurred. Find the required generation for each plant and the power received by load when the system lambda is 22 rupees per megawatt hour. The cost function for both the plants are given 720 plus 16 PG1 plus 0.01 PG1 square rupees per hour, and for second plant 900 plus 20 PG2 plus 0.02 PG2 square rupees per hour. So plant 1 is connected to plant 2 and load is connected at the second bus. So in this problem the transmission line losses are given, so we need to consider the losses and solve the problem to find the required generation for each plant and the power received by the load. So the transmission losses are usually expressed as PL equal to P transpose B into P, where this P is PG1, PG2 up to PGN, and B is a symmetric matrix which is given by B equal to B11, B12 up to B1n and B21, 22 up to 2n up to Bnn. The elements of this matrix B are called the loss coefficients. So for a 2-bus system, in this problem we are considering only 2 bus. So for the 2-bus system, PL equal to PG1, PG2, this is the P transpose matrix, into the B matrix, symmetric matrix for 2-bus system is B11, B12, B21, B22, and this is P matrix, PG1, PG2. So expanding this matrix, you will be getting the formula to find out the transmission losses. PL equal to B11 PG1 square plus B22 PG2 square plus 2 into B12 PG1 PG2. So using this formula we can find the power loss. So considering this formula, and in this problem the load is connected at bus 2. So this PG2, the plant 2 generator, will not have any effect on the load. So B12 and B2 will be equal to 0. So here B12 is the loss coefficient from plant 1 to plant 2, but the load is connected at bus 2, so this B12 and B21 is equal to 0. Also B22 is also equal to 0. Therefore the above formula is reduced to PL equal to B11 PG1 square. So this gives B11 equal to PL by PG1 square. So and in the problem it is given PL is 10 megawatt and PG1 is 50 megawatt. So 10 by 50 square equal to 0.004. This is B11, the loss coefficient. And now we are going to find the incremental transmission loss for bus 1. For that we are going to differentiate this PL equation with respect to PG1. So that gives you incremental transmission loss ITL1 dou PL by dou PG1. So that will be equal to 2 into B11 PG1, and second term there is only PG2 term, so this term will be 0, and the third term 2 B12 PG1 PG2, if you differentiate with respect to PG1 it becomes 2 into PG2 B12. So substituting B12 is equal to 0, so you will be getting 2 into B11 PG1, and we know this B11 value from the previous step, so 2 into 0.004 PG1. So this is the incremental transmission loss for bus 1. And incremental transmission loss for bus 2, differentiate the PL equation with respect to PG2. You will get 2 into B22 PG2 plus 2 into B11 PG1. And here you will be having B22 and B12. Substitute this value as 0 from here. So the incremental transmission loss for bus 2 will be equal to 0. Next, the incremental fuel cost of bus 1. So incremental fuel cost will be simply we are differentiating the cost function of plant 1 with respect to PG1. So if you differentiate, the 720 is constant 0 and 16 PG1 differentiation, you will be getting 16, and 0.01 PG2 PG1 square differentiation 2 into 0.01, you will be getting 0.02. Similarly, incremental fuel cost of bus 2, differentiating this C2 equation with respect to PG2, so you'll be getting 20 plus 0.04 PG2. So we calculated this incremental transmission loss and incremental fuel cost to substitute in this optimum operation condition. The condition says that IC1 divided by 1 minus ITL1 equal to IC2 divided by 1 minus ITL2, that will be equal to lambda. So substituting the previous equations, ITL and IC, that will be equal to the lambda value is given in the problem, which is 22, and taking this first equation, 16 plus 0.02 Pg1 divided by 1 minus 2 into 0.004 Pg1 is equal to 22. Considering that, simplifying, cross multiplying, you will be getting this, and from here multiply this 22 inside the bracket, it becomes 22 minus 22 into 2 into 0.004, that you will be getting 0.176, bringing that minus 0.176 Pg1 to this side, it becomes plus 0.176 Pg1. Adding with this 0.02, you will be getting 0.196 Pg1, and taking this 16 to that side, it becomes minus 16. So simplifying this, you will be getting Pg1 equal to 30.612 megawatt. And now equating the second term, 20 plus 0.04 Pg2 divided by 1 minus 0 equal to 22. So this gives you 22 minus 20 divided by 0.04, that will be equal to 50 megawatt. So the power generation will be Pg1 equal to 30.612 megawatt and Pg2 equal to 50 megawatt. Second, the problem they asked to find the power received by the load. So for that we need to calculate the power loss also. So power loss PL is equal to B11 Pg1 square. So B11 is 0.004 and Pg1 we calculated now for the optimum operation. So that is 30.612. Substituting, you will be getting power loss as 3.748 megawatt. Now power received by load PD is equal to Pg1 plus Pg2 minus PL. The generation minus loss, that gives you the power demand. So 30.612 Pg1 plus 50 Pg2 minus PL 3.748, that gives you 76.863 megawatt. So the power received by the load PD is equal to 76.863 megawatt. So this is how we need to solve this problem, considering the losses and using the optimum operation condition with the help of incremental cost and incremental transmission losses.